At the Large Hadron Collider, particles are smashing together at almost the speed of light. But how do scientists even begin to predict what's going to pop out of that chaos? Well, today we're diving into the master formula that brings a little bit of order to some of the most violent events in the universe.
To really get a feel for the challenge here, just imagine this. You're trying to predict the exact path of one little gust of wind that's whipping around inside a massive hurricane. I mean, it sounds basically impossible, right? And that's pretty much the problem that physicists are up against. They need to calculate a super precise collision between these tiny particles called partons, which are just swirling chaotically inside the much larger protons that they're smashing together.
So here's our game plan for how we're going to crack this whole thing open. We're going to start with the messy reality of hadron collisions. Then we'll pull back the curtain on the elegant formula that physicists use to tame it all. And finally, we'll break down its three key ingredients, piece by piece, so you can see exactly how it all works.
So first things first, what is the hadron collision problem? Well, it all boils down to a simple but very messy truth about what particles like protons are actually made of.
You see, when scientists smash two protons together, they're not just colliding two clean, simple billiard balls. No, not at all. They're smashing together two chaotic, swarming bags of quarks and gluons, and we call this whole mess partons. This incredibly complex internal structure is what makes the physics so tough, because you just never know which two partons out of that entire chaotic mess are the ones that are actually going to collide. So how on earth do you get a clean prediction out of that kind of chaos? How do you zoom in and isolate the one specific interaction you actually care about? Well, that's where this beautiful piece of physics comes in, the factorization formula.
Okay, whoa, don't worry about all the symbols. I promise, the core idea here is actually incredibly clever and elegant. It's called factorization, which is really just a fancy way of saying we're going to separate the problem into two parts. One, the messy, unknowable physics of what's going on inside the proton, and two, the clean, calculable physics of the one specific collision that we actually want to study. In fact, this whole scary-looking formula really just boils down to three key ingredients. First, you need a way to describe the inside of the proton. Second, you need a way to describe the actual collision. And third, you need a couple of little tuning knobs to get all the details just right. So let's tackle them one by one.
Our very first ingredient is something known as the parton distribution function, or for short, the PDF. So what is a PDF in this context? No, it's not a document file. It's more like a probability map. It's what helps us answer the question, if you could somehow freeze frame a proton and reach inside, what are the odds, what is the probability that you'd pull out an up quark that's carrying, say, exactly 30% of the proton's total momentum?
And this isn't just a convenient analogy. I mean, the physics is really clear on this. These functions literally represent the probabilities of finding a certain kind of parton inside a hadron, carrying a very specific slice of its total momentum.
You can almost think of the PDF as a recipe or maybe a probability pie chart for a proton's momentum. It tells us, on average, how all that momentum is shared between all the different ingredients. You've got your main valence quarks, a whole sea of other virtual quarks, and of course, all the gluons that are holding the whole thing together.
Okay, so the PDFs tell us the odds of finding the right particles for the collision. The second ingredient tells us what happens when they actually interact. This is the parton cross-section. Now, this part of the formula, the parton-level cross-section, this is where the real physics happens. Cross-section is just a physicist term for the probability of some interaction taking place. So this part of the equation calculates the odds that the two partons we picked out with the PDFs are going to interact in just the right way to produce the thing we're looking for, maybe something like a Higgs boson. And this distinction is absolutely crucial. The overall hadronic collision, that's the big messy storm, but the partonic collision is the clean, focused, calculable event happening inside of it. And you know, as the source material points out, physicists even use that little hat symbol in their equations just to signal that they're talking about that specific, clean, parton-level interaction. Okay, so we've got the probability of finding the partons, and we've got the probability of them interacting. This final ingredient is a little more subtle, but it's just as important for getting an accurate result: the physics scales. The first one is called the factorization scale. A great way to think about this is like the zoom lens on a microscope. It basically sets the resolution for how we're looking at the proton, and it helps us draw a conceptual line between the messy, long-distance physics of the proton's overall structure and the clean, short-distance physics of the one collision we want to calculate. The second scale is the renormalization scale. Now, this one is all about the interaction itself.
Here's a wild fact about quantum mechanics. The strength of a force isn't actually constant. It changes with energy. So this scale is like the knob we tune to make sure we're using the correct force strength for the precise energy of our particular collision.
So let's just recap that really quickly. We've got the factorization scale, μf, which is our resolution for seeing the partons. And then we have the renormalization scale, μr, which is the energy scale for calculating the strength of their interaction. Two different scales, two very important jobs, both crucial for a precise prediction.
All right, let's put it all together and just walk through the logic. First, you use the PDFs to figure out the probability of grabbing the right kind of parton with the right amount of energy from each of the two protons coming in. Second, you use the parton cross-section to calculate the odds that those two specific partons will smash together and create what you're looking for. And finally, and this is the key, because this can happen with countless combinations of partons and energies, you have to sum and integrate over every single possibility to get your final total prediction. It's just an incredibly powerful way to bring order to absolute chaos.
At the end of the day, this factorization formula is the bedrock of pretty much every prediction made at the Large Hadron Collider. It tells physicists what they should see, which allows them to scan through trillions and trillions of collisions looking for any tiny little deviation, any super rare event that might signal new particles or new forces we've never seen before. And that really leaves us with a final thought. By so perfectly calculating the probable, what truly improbable new discoveries will this formula help us unlock next?